Okay, so here's an explanation of page 2. Question number 9 was actually answered on the previous page. Assuming no friction, what would be its speed at the bottom of the hill? And remember that because we assumed no friction, the speed was something over 200 miles per hour, which was unreasonable. Alright, so 10, how fast would we be going halfway down the hill? It's easy to say, well, I'm just going to take half of the speed, but it ends up not being, that ends up being not correct. Halfway down the hill, well, let me give you a little explanation of why. Here's starting from the top, here's starting from halfway down the hill. When he starts from the top, he has sort of more time to speed up because he's going slower. Here he's going faster, so this actually takes less time. So if you assume that he's going to have a constant acceleration, he's going to have less time to speed up, so this is not going to be exactly half of the speed he'll have when he gets down here. So we do know that starting halfway down the hill means the height from which he starts is half of the original amount. So it's the same situation where we say potential energy equals kinetic energy, where height is this. So height mgh equals 1/2 mv squared, and we solve and get something like 73 meters per second. Okay, for the collision lab question, we're given position and we're given time for cart 1 and cart 2. So this looked something like this. We had a track, and it looks like cart 2 is at rest. So it looks like cart 2 is a little bigger. And then cart 1 is like this. So cart 1 is moving. We see how its position increases as time goes on, whereas cart 2 is just sitting there at 50. And then somewhere here, somewhere between here and here, the carts collide, and then notice how their positions increase, so they're both moving off to the right, and they're actually moving at the same speed. This is 2 less than this, 2 less than this, 2 less than this, 2 less than this. So at approximately what time does it look like the collision occurred? So that's somewhere between here and here. So if you said 0.2 seconds, 0.3 seconds, anything in between, that would be perfect. Velocity, so cart 1, what we're looking at is position and time. So distance divided by time. So before the collision, I chose these 2 points. If you wanted to choose these 2 points, that would work perfectly. I chose these 2, and we found this for speed. For cart 1 after the collision, so cart 1 after the collision, again, any 2 points, these and these, these and these, these and these, these and these, or these and these. So I chose these 2. So we have position, we have time. Notice how the position's in meters, and we got this for the speed. We're going to do the same for cart 2. Notice how the speed of cart 2 before the collision is 0. So 0 meters per second before, it wasn't moving, and then we do the same, pick any 2 points, distance and time, and we get this as a velocity for cart 2 after the collision. Okay, and then we are plugging in where we were told the mass in grams, so like 450 grams is 0.45 kilograms, and 650 grams is 0.65 kilograms. So speed before, speed after, speed before, speed after, we just calculated these. We're multiplying speed by mass to get momentum, speed by mass to get momentum, etc., etc. So what we can say is that the momentum of the system, meaning both carts, before the collision is this plus this. And the momentum of both carts after the collision is this plus this. What we expect is that momentum to be conserved. We say that momentum is conserved in all collisions. So momentum before equals momentum after, and we have 0.549 equals 0.550. So within rounding, that is excellent. was kinetic energy conserved. So look at how we calculate kinetic energy. This in here is a 1/2 mv squared. So 1/2 mv squared, 1/2 mv squared, 1/2 mv squared, and 0. And then when we go to calculate the total kinetic before and total kinetic after, because it looks like the carts stick together, so one of them had a position that was slightly greater than the other one, but they were moving at the same speed. So because they stick together, we assume this is an inelastic collision. Remember, elastic is bounce. And because it's an inelastic collision, we assume the energy will be lost. And check it out, that actually works. The energy before the collision is more than the total energy after the collision.